Hey everybody, I'm Phil Georgakakos, and I'll talk to you today about a project that is underway to quantify the potential for streamflow depletion from cannabis agriculture in California's North Coast streams using storage discharge sensitivity functions. And this work is done by myself, Chris Dillis, who you just heard from, Ted Grantham in the CRC, and then also David Drawley, Jesse Hom, and Dana Lapidis. So we were really motivated by some foundational work by Scott Bauer and Jen Kara in 2015 that suggested that diversions for cannabis agriculture might seriously impact these coastal streams that in particular support populations of salmon. And this motivated our question is, how does water extraction, cultivation influence headwater streamflow? And one major component of this is trying to understand the contribution of groundwater to streamflow. So groundwater's impacts is pretty hard to measure for a number of reasons. The first is that you can't really directly measure groundwater, right? It's under the subsurface. There's no way to easily access it. Wells are point sources on a landscape, and they're really expensive to drill. There's time lags between water withdrawals and potential impacts to stream flow. Individual basins can have like mixed lithologies, and that complicates the subsurface dynamics within those basins. And headwater catchments are pretty different from lowland systems where a lot of hydraulic models were developed. And those models are now being applied in headwaters where they might not be as relevant. So groundwater is also important because it drives most of the stream flow in coastal California. This is a hydrograph from the South Fork of the Eel River for multiple years. Each of these peaks correspond to discharge associated with a precipitation event during our winter rainfall season. And then during the summer drawdown period, stream flow is entirely driven by the hill slopes draining groundwater, which creates discharge during that time. And if you think about kind of California, all of these blue points on this map are drainages that have that type of hydrograph. They're fed by rainfall and then groundwater during the summer season. And it's also relevant because we know by work from Chris and others that a lot of cultivators are using wells to irrigate their crops, specifically in arid areas like southern Mendocino County, where you can see these dark numbers correspond to up to 80%, 80 to 100% of farms are using wells as their primary irrigation source. So where do these storage discharge sensitivity functions come in? So here I've kind of have two illustrative hill slope cross sections that represent two different time points. The first time point is on the top hill slope here, and you can see that there's a lot of that dark blue saturated zone water that is driving discharge. And if we go to time step 2 here, you can see that that water table has receded naturally from evapotranspiration and discharge draining the hill slope. But you can think about the impact of pumping water from that groundwater table, where that dashed blue line might represent the water table if pumping hadn't happened, and the solid line shows where pumping does happen. And the storage discharge sensitivity functions are represented by the curve in the middle there. They relate stream discharge with landscape level storage with the sensitivity function G of Q, and that's a clever way to kind of relate measurable stream discharge to groundwater storage in the landscape and kind of go back and forth between those two things and make predictions about how the hydrograph will proceed over a given period of time. And this is kind of a clever mathematical way that circumvents a lot of those hydraulic problems in other situations. And these were developed by James Kirshner and have been widely applied by my colleague David Drawley in other situations. So our study design was to really create a number of hypothetical situations that represent different parameters that vary in cannabis agriculture on the landscape. So we're using these storage discharge relationships to make synthetic hydrographs that varies water source, whether farms were pumping water out of groundwater or using surface water diversions. Farm water use efficiency, we see a wide range of farm water use area normalized efficiency. And so we wanted to represent some of that variation. The area of cannabis on the landscape, different lithologies, and then California has an extremely variable climate, and we wanted to encompass some of that variability as well. I'll go through each of those parameters just like super briefly. Farm water use efficiency, this is modeled by Chris Dillis et al. And You see a large range in farm water use. Each of these box plots are shown for months of the year, including the cannabis cultivation season. If we expand one of those months, like August, where you see the highest modeled water use, you see a distribution of all of these farms on the landscape. And what we did was we picked the 50th, 75th, 90th, and 95th percentile, represented by those little blue dots at the bottom of that histogram there. Aerial coverage of cannabis obviously varies across the state of California drastically. We looked in Mendocino and Humboldt County in particular, and we picked 5 different levels: 0.1, 0.25, 1, 2.5, and 4.5% cannabis agriculture by area on the landscape. And really 1, 2.5, and 4.5 are very high values. They might not seem very high, but those are really high values of aerial coverage of cannabis. But just keep that in mind as we're going through some of the results. For lithologies, we have this, we were lucky to work in 2 streams that have been very well studied hydraulically, and these are Elder Creek and Dry Creek. Both are in the greater Eel River drainage, and they're about 15 kilometers apart, so they share a climate, but they're separated by this lithological contact zone here. Elder Creek is in the coastal belt. Dry Creek is a little bit more eastern and in this melange, and that leads to different watershed characteristics. I'll describe those super briefly here. On the right of these hill slope cross sections, you have Elder Creek, which has a relatively thick weathering profile of its soils, and that leads to high landscape level storage capacity of that landscape. And that means that Elder Creek is a perennial stream. It has persistent summer flow. You have mixed conifer forests, so there's vegetation differences in these 2 drainages. If you compare that to the left, these images here, you have Dry Creek, which has a relatively thin weathering profile that leads to a very flashy stream, and it's kind of like grassland, oak savanna type habitat. Okay, so those are our kind of the different parameters that we involved, and we combined all of those parameters pairwise to create synthetic situations, and that resulted in like 336 hydrographs that I'll kind of summarize briefly. I'll pick out a couple to talk about these results. Okay, so these are hydrographs. This is kind of the results of these storage discharge sensitivity functions. These are hydrographs that are synthetic for both Elder Creek on the left and Dry Creek on the right. Our different lines represent different scenarios. So the blue line is just measured discharge in both of our streams. The dashed orange line is our modeled hydrograph. So you can see that that tracks the blue line pretty well, which we were excited about. That means our model performance is pretty good. The green line represents an impaired hydrograph that's entirely due to cannabis farms pumping water from the groundwater table. And then the red line represents direct surface water withdrawals by farms to irrigate their crops. So in these scenarios, this water year is representative of like 2017, a median water use rate and 2.5% cannabis cover on the landscape. And you can see that Dry Creek, our melange stream, goes dry every year just under natural conditions, but this level of water withdrawals greatly accelerates that drying. In Elder Creek, 2.5% cannabis cover on the landscape is enough to de-water this historically perennial stream that's never been observed as intermittent during the summer season. And another interesting thing to point out is that the effects of surface water withdrawal are accelerated compared to groundwater withdrawal, which we might expect. If we decrease the percent cannabis cover on the landscape to 0.25%, so a tenth of the previous picture, you can still see that in Dry Creek, there are pretty substantial impacts with accelerated drying. And in Elder Creek, there are impacts, but they're a little harder to see because they're proportionally less so. We can make other comparisons like water use efficiency. So I'm comparing the median water user on the left here to the 95th percentile water user, a less efficient use of water. And you can see that this is kind of to me, a little bit of a symbol for hope that if we can use irrigation practices that are a little bit more efficient, we can greatly reduce the environmental impacts. The lines are closer to, the modeled use in this lower impact situation. We can aggregate these findings to think about some other response variables like the total percent reduction in summer flow. So here the dashed line represents surface water extraction and the solid line represents groundwater extraction for both of our drainages. We've got percent aerial coverage of cannabis agriculture on the x-axis and percent reduction in summer flow on the y-axis. And you can see that in those really high coverage situations, there's really large reductions in summer flow from cannabis agriculture. But more realistically, these are the values that you see more typically on the landscape. And what's harder to see here is that Dry Creek actually responds more rapidly to any sort of extraction than Elder Creek does, meaning that it's more sensitive. This is that same data plotted in a slightly different way. So here I've plotted initial flow value on the x-axis, which is representative of water year. So values on the left of the x-axis would be like a very dry year. Waters on the right would be, or values on the right would be representative of a very wet year. On the x-axis, we've got an effective pumping rate, which is the area of cannabis times the extraction rate. So warmer colors represent higher impacts relative to cooler colors. And what you can see, those warmer colors are kind of concentrated on the top left of these plots, showing that in very dry years with lots of pumping, you see high impacts. But I think what this plot emphasizes is that there's a large effect of water year type. In a very dry year, you might have a very big effect, and on a very wet year, you might see a relatively much less effect. So that's worth kind of taking into account as we try to regulate these systems. We can look at other response variables like number of additional zero flow days, and those trends kind of match the percent reduction in summer flow, with the caveat that Dry Creek goes dry every year. So you see this kind of effect saturate rather quickly. Okay, so here are just some conclusions to keep in mind as we move forward. The application of these storage discharge sensitivity functions might be particularly useful in these headwater catchments where cannabis agriculture happens. They could be applied to all sorts of other agricultural products as well. Lower initial conditions, meaning drier years, higher coverage of cannabis, higher pumping rates, and extraction from surface water rather than wells all lead to lower summer discharge and more days of zero flow. Milan streams, that's our Dry Creek, was more sensitive to water withdrawals compared to Elder Creek, and that resulted in accelerated drying and greater impacts from similar withdrawal rates. Like I mentioned, there's a wide variation in cannabis irrigation efficiency, so there's a lot of work that could be done to kind of optimize that, including on-site storage, which might decouple plant demand from extraction time of water from these water sources. And then pumping's effect is expected to be delayed relative to surface water diversion. But I'll just say that, this might seem like I'm kind of advocating for pumping rather than surface water diversions, but there still might be kind of like important impacts that we should consider from groundwater extraction. Like there's other ecosystem level impacts like the plants that rely on groundwater tables. And this method really integrates effects over the watershed level. And we know that farms are clustered on the landscape, and the spatial distribution of those farms matters too. So this is a useful method when you're thinking about the watershed level, but there's also smaller scale spatial impacts that are important. And with that, I'll acknowledge, thank the UC-NRS system, the CRC for all of these collaborations that it's been facilitated. It's been really great to be a part of this group. The Department of Cannabis Control, which funded this work, and the Eel River Critical Zone Observatory. And I'll take any questions.